I will begin with a word of prayer. Dear Father, we thank you for this day again, Lord. I thank you for these students, and I just ask you to bless our work today, Lord. In your name I pray. Amen. Yeah, so I had a birthday party this Saturday, and for some reason my son Isaac, he has these shirts with ties on them that he loves to wear, and so the birthday party was a tie birthday party, and he asked me if I would wear this to work next week, and I said, yeah, sure. So here I am. Okay, so if you're wondering, you may still be wondering, I probably don't have a really good explanation for you, although it's been popularly agreed upon that this is what I should always wear going forward. Although I feel like if I agreed to always wear a gorilla suit going forward, you probably would vote, like overwhelmingly for that. So I'm not sure how much I believe in democracy choosing my wardrobe. Well, it's kind of fun to think about. Did I ever tell you guys about the pirate captain? No. So I think it was when I was in grad school at NC State. A guy ran for student body president. See, they were not careful with their bylaws, and they didn't say you had to run under your real name. And so he didn't. He ran in as the pirate captain. Needless to say, he won. And proceeded to go to all of the official, prestigious SGA events dressed as a pirate. And he refused to debate anything except in terms of pirate lingo. Everything was in terms of ER and so forth. He committed to it. Of course, I didn't vote for him because it goes against a more basic rule I have, which is to never involve myself in student government of any kind. But although, it was close. You have to admire that kind of commitment to a joke. Anyway, so this is not wrong, but this is not right. So what's not right about it is what? We should use the chain rule. So this is what happens when we don't use the chain rule. We get an answer, and okay, it's not wrong, but the chain rule here would be this. So we're supposed to calculate dz dt, all right? So the way the chain rule looks like here is partial z, partial x, dx dt, plus partial z, partial y, dy dt. You notice the total differential notation on the outside, because why? We're looking at a function which at its core is just depending on one independent variable, namely time, right? In contrast, problem 2, I asked you to calculate the partial derivative, and problem 3, I asked you to calculate the partial derivative, where at the center of the composition, we have not one independent variable, but two, u and v, all right? So when at the base of things, we have more than one independent variable, we're calculating partial derivatives. But even when at the base of everything, we have one independent variable, we might still need partial derivatives to sort through the chain rule, like here. So anyway, that is partial z, partial x is what? Oh, it's still ugly, but it's the log of x plus 2y plus x over x plus 2y by the product rule. And then dx dt is cosine t. And then plus partial z, partial y, which is just, it's 2x over x plus 2y. That 2 is there because of the chain rule with the differentiation with respect to y. And then my dy dt is just minus sine t. And that would be a good answer. Of course, we could put back in that x is sine t and y is cosine t, and when we did that, I think we would match up with what he has there after a little bit of algebra, I think. Yeah, like this is that sine t, cosine t. You see the sine t, cosine t term? That's that one is that. And the minus 2 sine squared term is that. That's this piece. And over here is the cosine times log. So it's all there. Whether or not you want to put in the functions of time, it really depends on the application and the question. Here's another one, problem 2. Calculate partial f, partial... Well, I said to calculate partial z, partial u. and partial z partial v, and I told you to go sit down because I forgot that you were half done. Sorry about that. My bad. It's all right. So here we go, partial f, partial x, partial u, partial f, partial y, partial u. That is the chain rule here because the intermediate variables are x and y, and u and v are the inside, the independent variables. And so partial f, partial x is y e to the xy, and likewise x e to the xy for partial y. There's that. The neat thing about this, guys, is partial v of, I could say partial z, partial v, is still going to be y e to the xy partial x partial v plus x e to the xy partial y partial v. See the partial f, partial x, and partial f, partial y are common to both partial derivatives, right? It's just the multiplying by partial x partial u and partial x partial y partial u change to partial x partial v and partial y partial v. In other words, these factors here are different, possibly. Like this one becomes 2v, right? And what's this? U, right? So it's, yeah. Now over here, this problem got a little bit more going on over there. We really have no, we cannot do the runaround that was done for problem 1 here, right? Just plug all the functions in and do plain differentiation isn't going to fly over here because you don't have functions to plug things into. All you got is data, right? So you have to use the chain rule. So here's the chain rule without the point dependence, with the point dependence suppressed. Partial w, so we're looking at w of f of u and v. So sometimes people will draw these tree diagrams to help make sense of things. May be helpful. I don't know. Oh. There's so many sarcastic comments in my notes, I lose track. But w, sorry. Then you got your, what you got here? You got your u, right? You got your v. And then below that, you have what? Oh, I forget how to draw these stupid diagrams. I have, how do you finish a stupid thing? I don't even remember. Yeah, I know, I don't remember how the custom is to draw these. I do not use these, so I do not remember. But they do help some people. Oh, that's not how they draw them anyway. Okay, I got it now. I got it. I'll draw it over here. So up here we've got our w. And then underneath that we would write partial w, partial u, and partial w, partial v. And below those we would write partial u, partial s, and partial u, partial t, I believe. And below these we write partial v, partial t, and partial v, partial, s, and partial v, partial t. And then, for example, this mnemonic for some reason is helpful to people. So to understand this chain rule that I wrote down because, well, I don't know, I just understand the chain rule intuitively, personally. I understand it in terms of like conservation of partials. If there's a partial t here, there has to be a partial t over here. And you have to have a term that describes the change of each intermediate variable, which in this case is u and v. And that's pretty much what guides me writing this. But in this way of thinking, if I'm calculating partial w, partial t, I need one for this path, and I need another one for this path. So that's why I get partial w, partial t, and you have to multiply as you go down. Partial w, partial u, partial t, plus partial w, partial v, partial t. So that's the tree diagram way of coming up with these formulas. The rule is you make this diagram, and then when you're calculating the partial derivative of this with respect to a given independent variable, choose all possible paths to get down to the ones that have the end up with partial t at the end. So there's those two, that's why there's two terms. Yeah. So that's why I wrote this. Actually, it's not. I just understand this. I don't need that stupid tree diagram personally. But anyway, enough about the trees. I don't want to speak ill of trees. You never know. Al Gore might be watching. It's totally unnecessary. Sorry about that. I mean, but maybe he'll be a visitor. Maybe no. I'm thinking for like the graduation this year. He might be an honored guest. I mean, if there's going to be Jimmy Carter, it makes sense that he would be, like in his entourage or something, right? He could fly his 737 in here, rent out a suite, like a whole, like level of some hotel around here, whatever. Go for it. Anyway, here I'm not really an environmentalist. I don't really know how to live. So what can I tell you? So partial W, partial T, 1, 0. So I have to put in the dependence, right? So this is at 1, 0. So the U and T in partial V, partial T are also at 1, 0 because they're both functions of S and T. All right, and then the partial U, partial F, partial U, and partial F, partial V have to be evaluated at their intermediate variables, which in this case is U and V at the 1, 0. Now UV of 1, 0 and V of 1, 0 are given to be 2 and 3. Right? So that's why we have partial F, partial U, 2, 3, partial F, partial V, 2, 3, which your benevolent instructor has told you the values of those partial derivatives of the outside function at the intermediate variables to be minus 1 and 10, like so. So then you multiply those by the 6 and the 4, which are also given, and we get 34. Yay. Make sense? Now, how do I make sure that I can test this problem properly? So you're like, I can do this problem. You're just going to give me a bunch of numbers. I can pretty much tell how I can have to multiply them together to get the answer, And if I just write sloppy enough, you won't be able to judge my work, right? Right? So there's a simple way I can throw a monkey wrench in your plans. It's very simple. I just add a piece or two of irrelevant information, right? That's all I got to do. Just, by the way, there's a monkey named George, and he's 6 feet tall, sitting in the corner, something like that, except with numbers and letters.
I mean, you kind of did that, didn't you, with the VS and the VT?
Oh, that's true, but this is just half of the homework example. In the homework example, I also say calculate partial W, partial S, but your point is well taken. I've already kind of done that with the way I've written it up here. You're right. You have to know which part of this matters to that, yeah. Very good. So any questions about the chain rule before I go on? The next section in my notes is how to calculate the normal and tangent vectors to a tangent space, but we've already done that, right? So what comes after that? Is differentiation with respect to side conditions. All right? That's the next topic. Past just garden variety chain rules and what more I have to say here involves things I'm not supposed to talk about, so I should probably stop talking about the chain rule at this point and go on to the next topic. There is one thing I should talk a little bit about, which is a possible confusion that we sometimes labor under. So here's the possible confusion. Sometimes, every so often, you'll see this versus this. All right? And so here's a place, possible confusion. And so here's the context in which that would happen. Suppose you were looking at, say, a function of two variables, right? And suppose you're also looking at y equals to, say, g of x, right? So you're looking at a graph. Then you might talk about df dx to mean what? This might mean ddx of f of x, comma, g of x. right? And how would you actually calculate that partial derivative? Well, this would be calculated partial f partial x dx dx plus partial f partial y dg dx. So in this single expression, you see you have df dx appearing, but you also meaningfully have partial f partial x appearing. Why is this happening? It's because I've used x in two different ways, right? I've used x both as the intermediate variable for f of xy, but also as the independent variable for the underlying path. To remove this confusion, it's pretty simple. If this is confusing to you, all you got to do is instead say, well, I'm not going to, you shouldn't use x in two ways like that. That's not nice to the students. So I should instead talk about df dt. What I really mean by that is d dt of f of t, comma, g of t. Right? That's really what's meant. And so here I'm looking at x equals to t. I'm looking at y equals to g of t, right? And so then the chain rule says, well, that's partial f, partial x dx dt plus partial f, partial y dy dt, right? Which in this context is really just partial f, partial x plus partial f, partial y dg dt. So this is the way that you could end up seeing a derivative, a total derivative with respect to x, and a partial derivative with respect to x, both appearing in the same expression in a way which wasn't crazy, but at the same time was annoying. Okay? So you've been warned. This doesn't happen too much, but there's like an application or two out there which just kind of like will corner you into making this notational confusion if you're not careful. All right? It's not a big deal, really. Here's a bigger deal. So this is differentiation with respect to side conditions. All right. Here's what I mean. Something like this. Suppose that we have, let's see here, x squared plus y squared plus z squared equal to, 3. And we also know that xy is equal to z. So I want. I should learn by now not to make up my examples. I do have notes for a reason, Let's see here. What I wanted was... come on. Let me try this one. Sorry, guys. It's the worst thing is when you can't think of the problem, Did I ever tell you mathematicians are only happy when they have problems? It's true.
They're not happy when they have problems.
They have problems with their problems. That's the problem at the moment. It's true. It's true. Let's see here. So this is my example in my notes. Let's see if we can, maybe it'll help us out. W equals to x, y, z. All right. Oh, it's still not what I want. Son of a gun. Just a second, guys. Ah. You know what? Let's just talk about this tomorrow. What do you say? That sound better? I mean, why suffer? Go about your day. Enjoy the time.